And now we have an example of complex conjugate roots coming out of the characteristic polynomial. So let's take our differential equation to be y double prime plus 14y prime plus 50y equals 0. And for this one, we'll see the characteristic polynomial looks like r squared plus 14r plus 50. And so when you go to factor this one, you notice, okay, so that doesn't really seem to factor. What do? Okay, well, I can fall back on the quadratic formula. So we go to the quadratic formula, and this is going to be minus 14 plus or minus, and then we have the square root of 196 minus 200, all divided by 2. And so this gives you minus 7 plus or minus 1/2. And then when we look in the radical here, what's going on underneath that is we have minus 4. And so the minus 4 we think of as a minus 1 times a 4. And so when we work out the square root, the 4 comes out as a 2, and the minus 1, the square root of that is I. So this is going to be times 2i. So we get minus 7 plus or minus I as our roots for this one. Okay, what do we do to make sense of that? Well, let's see. So our solution ought to be something that looks like minus 7 plus or minus, let's just say plus for right now. We'll just look at the positive root times x, right? And this is e to the minus 7x times e to the ix. Now this part that we've got out in front here, this is fine. We know how to deal with that. This latter part here is a bit of a mystery, so we just need to know how to deal with this guy. All right. Well, luckily, there was a bright Swiss guy called Euler, and he worked out what we should do with this. And it turns out that if you look at the power series for the exponential, and you put ix in for x, and you see what happens with this thing. Well, let's see. So there's these powers of I in there. Now this part right here, that actually just looks like the terms for the regular e to the x, right? So what about the other part there? Well, if we look at the powers of I, you get, so I to the 0 is 1, and then I to the first power is just itself, and then I squared is minus 1, and then I cubed is going to be I times I squared, so it's going to be minus I to the fourth, that's going to be I squared squared, so minus 1 squared, so that's 1, and then, oh god, we're back where we started. And so there's this repeating pattern that looks like this of order 4. And so let's see. So in particular, every other term is real and every other term is complex. And so I can split this now into, let's have the evens and the odds. So we'll have the evens be here. So this is where we have x to the 2k and I to the 2k, and then we'll have the odd terms from the series. All right, now we're getting somewhere, so let's see. So if I look at the even terms, I to the 2k, this is the same thing as I squared raised to the power k, but I squared is minus 1. So that first one becomes minus 1 to the k x to the 2k over 2k factorial. Okay, for the other one, if we look at I to the 2k plus 1, this is the same thing as I times I to the 2k, which we just worked out in the previous step. So it looks like that. So I'm going to take that one factor of I right here, and I'm going to write it out in front of the series. And then the rest I'll put inside. And so we have minus 1 to the k x to the 2k plus 1 over 2k plus 1 factorial. And then if you remember your Calc 3, this is the power series for the cosine of x. And this is the power series for the sine of x. So we now have a lovely way to make sense of our formula here. So y1 is going to be e to the minus 7x times cosine x plus I sine x. And that still is sort of dissatisfying, right? Because how are you going to plot something like that with an imaginary argument? And I guess here's the other one. y2 is going to be e to the minus 7x. And this will be the one where we have a minus sign there. So if I put in y2 equals e to the minus 7x e to the minus ix, then when we come down here, I have cosine of minus x, but cosine of minus x is the same thing as cosine of x. And I have sine of minus x, but sine is an odd function, so that's the same thing as minus I sine of x. Okay. And so our general function is supposed to be c1y1 plus c2y2. So that's c1 e to the minus 7x cosine x, c1 e to the minus 7x sine x. Oh, I forgot my I. And then from the y2 we have c2 e to the minus 7x cosine x minus c2 e to the minus 7x I sine x. And now I'm going to group the cosine and sine part together. So I'll have for the cosine parts c1 plus c2 and for the sine parts I'll have I c1 minus c2 and then I look at this and say, you know what, this thing in the box, this is just a constant, right? Some arbitrary constant, and at the end of the day I'm going to find out the value of that constant by evaluating some initial conditions. So I'm going to call this constant k1, and the same is true for this one, because the imaginary number, it's just a scalar, it's just a constant. So this is going to be k1 e to the minus 7x cosine x and k2 e to the minus 7x sine x. And you say, wait, can you do that? That's an imaginary. But yeah, you know what? It's just a constant. So there. Oops, what am I doing? There we go. Okay, and that'll do. There is our solution. Okay, so I went through the big hairy derivation and everything, and we looked at all three cases. You don't have to derive those from scratch at any given moment. All you need to remember is this formula right here, so that in the case of distinct real roots, we have a sum of exponentials. In the case of a repeated real root, we have a polynomial times an exponential. And in the case of complex roots, we get sines and cosines. So we get oscillating things. And that's something that's worth remembering in general. Whenever you have something that's oscillating or rotating, that's when complex numbers come up. And if you recall, when we had complex eigenvectors for matrices, those showed up when we started looking at matrices that corresponded to a linear transformation involving rotation. Not a coincidence. Complex numbers are how we write down rotations. Okay, so that last formula there shows all the different kinds of things that can happen when we're looking at a constant coefficient, homogeneous, linear ODE of order 2.